Hey guys, now I'm gonna switch gears. We're gonna get away from volcanoes. We got two units. I'm gonna try to compress them into the last couple weeks of school for you. This next one is going to be on earthquakes. So when we're talking about earthquakes in science, we talk about stress. And stress is, in science, it's basically just putting about enough force in a given area. And so when we do it in rock, we can actually see deformation, and that rock is bent, and we can actually bend rock. And so where does it happen? Well, we've talked about these plate boundaries a lot, and so this is where we get a lot of stress that builds up when those two plates are hitting. They're going away from each other. They're going underneath. It can create all kinds of stress. So we've talked about compression. Compression happens at these convergent boundaries. Okay, tension is the opposite of that. This is at a divergent boundary. Stress can be on something. Think of like a rubber band. If we stretch it too much, eventually it will break, and that breaking is what would cause the earthquake. So we get these different folding in the rock. Don't worry about this stuff for now, but this just shows like these would be different layers in the rock, and we would see um, roadside cutouts like these where we would see the rock has been bent and stressed and folded over time. So, well, an earthquake is eventually when this actually breaks, and we have something called a fault line. And so this fault line is where that break actually occurs. And we have two different parts. One's called the hanging wall, one's called the footwall. Don't worry about that for now, but these are all the different faults that are around the world, and you can see they're everywhere. And okay, so this is we have different kinds of faults that occur. So when the rock breaks, the different sides of that fault line are going to move in particular ways, different ways. Okay, so I'm going to I usually have animation on that thing, and it's not working. But basically, if we get this tensional stress and it's pulling apart, if one side the footwall goes up, that's called a normal fault. Okay, and then the hanging wall goes down. All right. Well, that's a normal fault. Well, then we have something called a reverse fault, and a reverse fault is the opposite of that. The hanging wall goes up and the footwall goes down, and this is caused by that compressional stress. So I'll show you guys some animation as this works out. And in Klamath Falls, around Klamath Falls, we've had lots of earthquakes, and we've had these breakings happen locally. And so if we if you've ever driven along Klamath Lake and you've seen those steep sides to the lake, like if you're driving north to Chiloquin, you can see that is a footwall that has gone up that steep embankment. And then the last kind of fault breaking, instead of rock going up and down, we have rock that breaks side to side laterally. Okay, and this is called a strike slip fault. And so the rock is breaking this direction, not up and down. And so these cause all three of these we can get earthquakes. And so what causes an earthquake? Well, let's watch this short little video.
Earthquakes are caused by powerful geologic forces rarely visible on the surface. For example, the rocks on either side of a fault may move only a few centimeters per year, but this movement produces enormous stress and strain in the rocks. As movement continues over years, or even centuries, stress and strain increase. More and more elastic energy is stored in the rocks. Along the San Andreas Fault, horizontal movement has taken place. By means of a diagram, we can represent the horizontal movement.
So it's a strike slip fault they're showing.
A cutaway view reveals that the underlying rocks have been displaced. We can also see the focus of an earthquake, the place beneath the surface where the rocks have ruptured. The location on the surface directly above the focus is called the epicenter of the earthquake. Maximum damage is most likely to occur at the epicenter.
Once rock breaks, it goes through these waves, and these waves travel. And there's three types. Let's see if this link will work. So this video is going to show us how these seismic waves move through rock.
Earthquakes generate two main types of seismic or shock waves: body waves and surface waves. Body waves travel through the interior of the Earth. The fastest of these are primary or P waves. These compressional waves move faster in dense rock and slower in fluids. Thus, their speed and direction change. Because they are deflected by the Earth's core, P waves are not seen in the so-called shadow zone. The slowest body waves are secondary, or S waves. S waves are elastic shear waves that move material sideways at right angles to their direction of travel. Because secondary waves travel only through solids, they do not penetrate the Earth's outer molten core. For this reason, there is also an S-wave shadow zone. The slower seismic surface waves do not penetrate the Earth's interior, but follow the surface. One type of surface wave, the love wave, travels in a circular motion and causes damage by displacing materials horizontally. Love waves can be very damaging. This cracked pavement and these twisted railroad tracks clearly demonstrate their destructive power. Earthquake damage also results from Rayleigh waves, surface waves which deform materials vertically.
So to review from that short video, we have P waves, and these are pressure waves or the primary waves. These are the first things. They travel super, super fast. Oftentimes, people may not even feel that P wave. Okay, S waves is a secondary or shearing wave, and this is the rock where it moves it back and forth, and it cannot travel through liquids, but it's half as fast, so it's a lot slower, and this is what people really feel, the rocking of the ground. The last one are called surface waves, and these move much slower, but these are the most destructive. And these kind of roll the ground up and down. So your P wave kind of goes quick through the rock. Your S wave kind of moves the rock side to side, but these surface waves move the ground up and down. And so you can kind of feel those sensations. I don't know if any of you have been in an earthquake, but I was actually in one of the biggest earthquakes in Oregon. Actually, the biggest. Did you know that Klamath Falls, that's right, kids, Klamath Falls has the biggest recorded earthquake on record. And it was back in 1993. And I'm going to put a link to this so that you guys can read this. Okay, there was actually two earthquakes that took place. The first earthquake was a 5.9, and shortly after that, I think around 10 at night, there was the second earthquake. And we often call it an aftershock, but the second earthquake was actually bigger. It was 5.9 at like 8 at night, and then it was a 6.0 at like 10 at night. And I'll never forget it. I was sitting on my stomach, flipping back and forth from Monday Night Football and Beavis and Butthead. Yeah, that's right. And I was flipping back and forth, laying on my stomach downstairs at our house, and just the ground started. I felt those surface waves, and it was crazy. It got up in the door frame, and so anyway, I don't know if you guys have experienced one, but in Klamath Falls, we have so many fault lines because if you remember, we talked about the basin and range, and the basin and range is splitting apart, and so we get this rock shifting around, and it builds up that tension, and it relieves itself, and we're kind of on the edges of that, and we get those earthquakes. What are some larger earthquakes that have been around? Well, this is the 1964 earthquake in Alaska. This has deformed the ground about 20 or 30 feet. So this was a 9.2 on the Richter scale, and look at this crazy damage. I mean, this is just bizarre, just unbelievable. Well, not only did it have the crazy damage, so look at the ground just completely fractured, and I mean that's someone's house totally on the side. But there was also a tsunami that followed that, and our last unit is going to be on tsunamis, and so we'll talk about that in a later video. So, and this last part that I forgot to talk to you guys about was about how earthquakes are measured, and there's two scales. One of them is a Richter scale. The other one is called the Mercalli scale. And the Mercalli scale is measured on a scale from 1 to 12. Listen to some of these descriptions. Sleepers awaken. That's a 5. A 6. People walk unsteadily. Number 7. Hanging objects quiver. Furniture is broken. And 8. Difficulty to steer motor vehicles. Well, I don't know about you. I've seen some people walk out of some buildings around Klamath Falls stumbling. I've seen people not driving their cars very well. So the Mercalli scale is not very good. It's the damage that the earthquakes do to things. The Richter scale, however, is much better. And I'm going to zoom in a little bit so we can focus on this part. But it's a mathematical measurement, and it's logarithmic, meaning from one number to the next, it goes up by a factor of 10. Okay, so 1 on the Richter scale means that it's 10 to the first power. A 2 means that it's 10 to the second power, so this means that it's 100 times stronger. If we have one whole number difference, the difference between a 6 and a 7, it's 100 times stronger. If we have a 2 number difference, a 1 and a 3, that's 1,000 times stronger. And not only with that, we can measure the amount of energy. And so the 32 times stronger for every whole number as well. So the Richter scale is a much, much better way of figuring out the strengths of these different earthquakes. Also, how many earthquakes happen every year? Well, I'm going to zoom in on this one again. So there's this bottom part, you can't see it, but earthquakes measuring less than 3 are not included because about 9,000 of those occur every day. What? But that's actually a good thing. So think about it this way. If these smaller earthquakes weren't taking place and relieving some of that stress, it would build up, build up, build up even more. And then when that rock finally breaks, there would be much, much stronger, much, much more energy. And so it's a good thing that we have these smaller earthquakes happening. But if you take a look, every year there's about 18 7 to 7.9 earthquakes, and there's usually one that is in the great category, and that's an 8 or higher on the Richter scale. So when we take a look at tsunamis, there's a prediction that one off of the Cascadia quake that scientists are predicting could be coming soon, is going to be one of these major quakes, and so one of these great quakes. And so we'll see how that plays out, and we'll talk about that on the next set of videos and assignments.